Intermittent computing promises long lifetimes for IoT edge devices. Powering these devices from energy harvesting allows them to be deployed and left, potentially for decades. These devices save their state before power failure to a non-volatile memory. It was the introduction of FRAM, with its much reduced time and energy overheads when compared to flash, that enabled this research to develop. My name is Tim Daulby, and I'd like to argue that as intermittent computing matures from proof of concept to deployable devices, we must evaluate the available non-volatile memory technologies and assess the impact of their characteristics on the schemes and devices that we develop. I'm therefore presenting a poster titled Comparing NVM Technologies Through the Lens of Intermittent Computation. I'll take the next 2 minutes to introduce my comparisons across 3 key metrics. The first of these is their energy consumption. Each of these comparisons will include flash and SRAM for comparison, as well as giving a scale at the bottom. In this case, each coin represents 100 picojoules of energy to write 1 bit, with some memories requiring less than 100 picojoules or much less than 100 picojoules, as indicated by the less than arrows. Most non-volatile memories have a high energy consumption when compared to the cost of clock cycles on a low-power CPU. This may motivate schemes that minimize the number of accesses. In addition, we see that many of these memories are asymmetric. Their writes are more expensive than their reads. This may motivate schemes that prefer re-execution over checkpoints. Secondly, latency. Here, we show the number of clock cycles needed on a 24 MHz CPU for NVM accesses. Many of these technologies have very similar numbers, but are much greater than SRAM. Many existing intermittent computing schemes employ unified memory approaches that replace RAM with NVM for faster checkpointing. However, these suffer performance loss that may outweigh the benefits, both in terms of the latency seen here and the energy cost for the accesses. Finally, we consider the write endurance of these technologies. Many of these technologies suffer from a low endurance. Taking the example of a Psycho watch power trace, which interrupts roughly every 0.4 seconds, FRAM could checkpoint successfully for 6.34 million years, if we ignored all the other factors. But ReRAM, with an endurance of 10 to the 5, would last only 4.63 days. I hope this short introduction has piqued your interest. You can find further detail in the associated paper, and I'd love to discuss this further with you during the poster session.